Uh, Hello everyone, good evening and welcome to another ELISA tutorial session. We are doing chapter 4 of electric drives, and hopefully this should be our last set of streams since we'll be completing very soon. Pray that God will see all of us through and that will be fine. Okay. Yeah. So as I said, we are looking at chapter 4. And chapter 4 talks about speed control. So we'll be looking at speed control. Speed control, how we can control speed in electric drive. Look at speed control in DC machines. Look at speed control in AC machines. And then we'll look at speed control in induction motors. Speed control in induction motors. Yeah. So let's quickly get into the slides and then let's see. Sorry about all this. Okay. So now let's talk about speed control. Okay. Now from this formula here, we know that speed control in DC. We're looking at speed control in DC machines. Speed control in DC machines. Let's take this formula. We know that speed is equal to what? V over K phi minus RATE over K phi squared. We know this formula, this speed formula, steady state speed formula. Right. Now from this formula, we can let's observe these two parameters. Let's observe voltage here and let's observe phi, flux. The two ways by which we can vary the speed or we can control the speed is by varying the voltage. That's the first method. Varying the armature voltage. Varying the armature voltage. And the second method deals with varying the field current. Varying the field current. Know that when we vary the field current, it has an effect on the flux, right? So if I have the flux like this, it's a function of IF. I increase the field current, I increase the flux produced in the field appreciably too. Now, we know that for any device or for any machine, we can't operate it above its rated values. It's not advisable to operate them above their rated values. So that means that I can't increase V, I can't increase phi. That means that only reduction is possible. Keep in your mind that only reduction is possible. So I can only reduce the armature voltage. Now let's see the relation here. I can see that omega is proportional to V. So when I reduce the armature voltage, what do? I reduce the speed. So a means of reducing the speed in DC drives is by reducing the armature voltage. That reduce the speed. Also, I can't also operate the machine above the rated field current. So I can't increase the field. I can only decrease the field. So here too, only decrement in field current is possible. So I can see that speed is inversely proportional to phi as a function of the field current. If I reduce the field current, I reduce the flux, and subsequently I increase the speed. So I can see that it means it's possible to achieve speed incremental and then speed decremental too. I decrease the speed by decreasing the armature voltage, and I increase the speed by decreasing the field current, which decreases the flux. Okay, so now from here, yeah, so basically that's it. So now we have to define a certain mid-range, right? I'm talking about increasing and decreasing. What specifies where we increase from, where we decrease from? There's a mid-range or a middle point or a reference point called the base speed. The base speed is the speed of the drive at rated voltage and rated field current without any external resistance. So no external resistance is in the circuit. That's the base speed. When I reduce the V, I reduce the speed below the base speed. And when I reduce the IF, I increase the speed above the base. Let me show this image. Okay. What do you say on the has it? So this is what the entirety of the DC control revolving around. Ways of reducing the armature voltage as a means of reducing the speed, and ways of increasing the speed by reducing the field current. Okay, so that's it. So let's come to the slides and let's see. So I've explained all this idea. So, oh, all right. So yeah, so from this equation, varying the flow current, I've explained all of this side. So we're looking at explain this side to that when you reduce the voltage, you reduce the speed, right? Now let's talk about something here. Let's talk about something here. Now we know that DC separately excited or shunt motor has its characteristics here like this, right? Where this is the no load speed, that's a V over K phi. V over K phi. We know that speed is what? R V over K phi minus RAT over K phi squared. So as no load means this is zero. No load speed is this from V over K phi. That's why it cuts it the other side. Now you realize that if I vary, so if I take this is a graph of what? Speed against torque, right? So this is like having y is equal to c plus mx gradient. So you can see that the gradient is this, is RA over K phi squared here. And the y-intercept is V over K phi, that's this here. Realize that if I reduce V here, it doesn't have an effect on the gradient here. It only affects the y-intercept. So reducing V just shifts this curve downwards like this. A new no load speed here. This is V1 over K phi, this is V2 over K phi. Now note that we are looking at reducing controlling speed of DC shunt or separately excited by varying armature current, by varying armature voltage, by varying the armature voltage. That's the topic we are looking at. Controlling speed of DC shunt or separately excited by varying armature voltage. So we are reducing the voltage. So a further reduction will cause the curve to come here. Until the curve, we can get the curve to cut this at this point here. So that's it here. So that's the effect it has on it. If I have a unidirectional torque like this, unidirectional torque load like this, you can see that at this point here, our TL and our TE intersect at this point. So this point is a steady state condition. And at this point, because the speed is zero, it's a holding condition. So holding condition, let's look at what holding condition is. Holding condition is a condition where TE is equal to TL, steady state, and also speed is equal to zero. It's holding. So at this point here, E is equal to TL, yes, that's correct. It's a steady state speed, but it's not a holding condition. At holding condition, it's a steady state speed, and also the speed is equal to zero. That makes sense, right? Yeah. So everything I'm speaking about account for this side. That the slope does not change. It's only the intercept that change, no low speed here. That's what changes here. And as you reduce the voltage, the speed reduces. So over here, V1 has a higher. So when I reduce it to V2, the curve comes down, and then so on and so forth. So that accounts for this side. Now, controlling speed of DC separately excited or DC shunt by varying armature voltage. That's what we are looking at. Sure. Now this can be done in two ways, right? We have a conventional method. Conventional method is like a traditional method. So that traditional method involves the use of resistors or generators to achieve the speed control. Before we have the solid state control method. The solid state control method will involve the use of the rectifiers like solid states, right? Rectifiers and converters, those like modernized circuitry systems. So first, let's look at the conventional method. Conventional method of the speed control of DC motors. Conventional method. The conventional method employs a system called the Ward-Leonard control system. Ward-Leonard control system. Ward-Leonard control system. Let's see how the Ward-Leonard control system works. So this is my motor, my separately excited motor whose speed I'm trying to vary. The motor will be connected to a generator motor set. Okay, to be connected to a generator motor set like this. So this is my generator. This is a generator driven by a motor. So driven by some motor somewhere, right? Of course, generator yes converts mechanical energy to electrical. So it's driven by a motor from somewhere, right? Yes. Now there is a constant voltage source here. So the field winding of the motor that I'm trying to control its speed picks its source from here. Picks its source from this here. This is my RF. This is my RF. This becomes my VF, right? Field voltage. Then it will cause some field current to flow through. That makes sense. So now also this generator also gets excitation. Generator field excitation from also comes from here. Now it is a variable field, right? So this one is goes through a variable field, and I'll explain why it's so. Something like this. I can't really draw it, but something like this. So we can vary it. The idea is that we want to vary the excitation of the generator. Varying the excitation of the generator has an effect on the what? On the output voltage on the generator. And that output voltage of the generator becomes the input voltage to this motor. Okay. So if I'm able to vary that voltage, that output voltage, it means I'm varying the voltage to the motor. And hence, once I can vary the voltage to the motor, once I can vary the voltage, I can reduce it, and hence I can reduce the speed of the motor. That's how the Ward-Leonard control system works. Vary excitation of the generator. To reduce the excitation, to reduce the voltage. As the voltage is directly connected to the motor. So as the generator output voltage is reduced, the motor input voltage is reduced. And a reduction in the motor input voltage will lead to a reduction in the speed. So that's it. That's the Ward-Leonard system. That's the Ward-Leonard system. You understand? So this field winding picks a certain electrical current from here, right? Input. Then a portion of it goes to the field, a portion of it goes to the armature, and comes as output. Right? Yeah, so that's it. So let's look at the Ward-Leonard system question in the slides. You see, so I'm just touching the salient point. So I've described the system here. Then the description is all here. That's the description here. So you read all through all the side. It can be to achieve the regenerative braking. Yes, so you read all advantage, disadvantage, just take your time and read. So this is the main point. This is what we want. Okay. So can you refer? So let's read through the question. In a Ward-Leonard control method of speed control, the variable voltage motor is separately excited from 500 volts supply. Motor output power is 450 kilowatts and its efficiency 90.0%. It is supplied at 500 volts from generator and runs at 400 RPM. If the motor is required to run at 200 RPM, so the motor is running at 400 RPM, a certain speed. Now, we want to reduce the speed to 200. And we say we can achieve that by what? Reducing the voltage. So the question is that determine the excitation required of the generator. This question, we are supposed to determine what excitation will give us some voltage that will cause this speed to reduce from 400 to 200. It makes sense, right? Yeah, it makes sense. Then in the question they gave us the armature resistance, the field resistance. They also give us the OCC characteristics. the open circuit characteristics of the generator. So here's how we go about the question. Okay. When they say find the excitation, you're talking about you finding the current here, right? Excitation current here. Because the excitation current, the flow current going through this generator winding is what we call the excitation. Find this flow current here. So we have a table here. So realize that if I'm able to find the EMF of the generator, if I'm able to find the EMF of the generator, that will give me that speed. I can just come to the curve and trace it and find the corresponding IF. Yeah. So the first step will be for you to just draw this curve. That's the first step. So you plot a plot of IF against E. The point between when you plot, you get something like this. It's just a plot. Yeah. If people will give a question like this, you can give us 2 points so that it's a straight line. Right? So if it's a straight line, you know how to find equation of a straight line and how to plot it. So if PY will give a question like this, it will give you just 2 points. Just 2 points. 2 points, right? So you can find the equation. So you know how to do y2 minus y1 is equal to m into x minus x1. And you find the equation. So you can plot this point here. So that the E you find, just substitute your E into that equation to find your IF. Okay. Now let's delve into the question. Let's delve into the question. Hold up. Okay. I don't want to clean the drawing. I just put the values into it. Question: we're given that what the variable voltage motor, that is this motor here. That's what we're trying to control. Is excited from 500. So this line is 500 volts. 500 volt supply. This motor has an output P out of 450 kilowatts, and efficiency is 0.9. It is supplied at, so this one is also supplied at 500 volts. Supplied at 500 volts from generator and runs at the initial speed. Let me call it NS1 is 400 RPM. If the motor, so NS2, no, not NS2, N1, N2. NS is for the induction motor synchronous here. N2 is 200. So when we reduce it to 200 RPM, determine the IF. They give us our RF to be what? RF is equal to, RF is 50 ohm. The field in 50 ohm here. Then our array, armature resistance of the RA of the motor, this motor is 0.01. Then the array of this also has its own array, 0.02. So we want to find this IF. Now let's find our IF here. I have to find the E and trace it on the curve, as I said. Now find this E of this generator here. I'll back solve. I can find this E of this generator here. And then this is supplying, so I'll just back solve to get this E here. Let's see how it works. Now I know VF, I know RF. I can find IF, true or false? IF. IF is what? IF is VF over RF. 500 volts over 50, 10 amps. IF is 10 amps. IF is 10 amps. Now let me find the power dissipated in the field. You see what we are trying to do here? P field, I squared R. I squared R. That's what 10 squared 100. 100 times 50, 500 watts. 500 watts. This is the power dissipated in the field. Now see something here. I have a motor. I have a motor here. This is the motor using input power. A portion of the power goes to drive the field, and a portion of the power gets to the armature. So if I know the P field here, and I want to find the armature, the power in the armature, let's follow. Let me find the input power. Let me find the total input power. I know output power 50. I know efficiency. I can find input power. P in is equal to P out over efficiency. 450 on 0.9. That's 500 kilowatts. Now I know input power. This is 450 kilowatt. 450 kilowatt. So I know input power. I know the power in the field. Find power in armature. Power that gets to the armature. The power that gets to the armature is given by what? Power that gets to the armature is given by power input PI minus power used up by the field. That will give me 500 kilowatt minus, this is 5. Okay. 500 kilowatt minus 5 kilowatt. That will give me what? 495 kilowatts. This is the power. This is the power that gets to the armature. Now, why am I finding this power that gets to the armature? I want to find the armature current. I want to find the current that goes to the IA. So I know power of the armature, right? So that what? P is equal to what? P is equal to IV. P is equal to IV, right? IV. So my I will be equal to what? P over V. So P is what? 495 kilowatts over voltage 500 volts. I'm finding IA. I want to find the current IA. So first I found the power here. We found the total power from here. Subtract it to get the power of the armature. Once I know PA here, I'm doing IA is armature power over voltage supplied. So that'll give me the IA. So let's count and see. So we are doing what? 495,123 divided by 512. 990 amps. 990 amps. 990 amps. I have the current that's going through the armature. Right now, I have current. Let me find the EMF, the back EMF of this motor here. E is equal to what? V minus IA. I don't want to click this because I'm referring to it. That's why I'm keeping this diagram here. So I'm sorry that it looks clustered a bit, but then just pardon me. Try and see something. Okay. Try and see something. Let's find out back EMF. E is equal to what? V 500 minus IA 990 times RA 0.01. So this will give me the E. This will give me the E at what? E at 400 RPM. This is the EMF, back EMF, yes. At what? At 400 RPM. So let's find it here. 500 minus 990 times 0.01. That's 490.1. E is equal to 490.1. 490.1 volts. Now in the question, we are supposed to find the excitation that will cause the speed to reduce to 200 RPM. So let me find the EMF of the motor. Let me call it EM. At the mean speed. So I know that what? I know that E2 over E1 is equal to what? N2 over N1. We should all know this. So E2 is equal to N2 200 over N1 400 times E1 490.1. So this will give us half. So half of the answer we got times 0.5. That should give us 45.05. 245.05. This is the motor, the back EMF of the motor at 200 RPM. Now, I have the back EMF of the motor. I have the back EMF of the motor. I want to find the excitation of the generator set here. I want to find the excitation of the generator set here. Are you following? Now, let's see. We know that E is equal to what? E. Now we are for a generator. For a generator, E is equal to V plus IA RA. We know that, right? Yes, this is motor. Yes, generator, it is the E. E is the E that's a portion of it dropped, and the remaining goes to the terminal of the generator. So E is equal to V plus IA RA for a generator. This generator here, the V of the generator is directly coupled to the motor. So the V of the generator here is what is giving us the back EMF of the motor. I can write a certain equation as E of the generator is equal to the EMF of the motor plus IA, let me call it RA prime. RA prime because this generator supply here is go through its own array here, and it's supplying to this motor. So the array of the motor will also have an effect on the total resistance. So EG, which is the excitation of the generator, is equal to EM. The EM, before it will be 245.05 plus IA was 990 times total resistance 0.02 plus 0.01. So that'll give us this here, the generator EMF. The generator EMF, as we can see from here. The generator EMF, as we can see from there. So now that I have the excitation, the E here, if I had drawn my curve, I told you you draw a curve. So if you draw a curve here, for that excitation of what is the excitation? 274.75. 274.75, somewhere around here. I'll come and match it to the IF, and I'll find the field current. Does that make sense? Yeah. So that's it. So if it was a straight line like this, let's just say the equation is y is equal to 3x plus 4. Let's just say, right? You can find the equation here. So y is equal to 3x plus 4. So now I'll have to come in. Oh, sorry. How do I want to do? See, this is a line. I want to cut it in through the point. That's why. This is a line. Y is equal to 4x minus 1. So for this line, I want to find the x value. So say when I got the E was somewhere around 200. So I'll put 200 in place here. You see, since there's no graph to actually draw, so it will be a sketch. So you have to work with the equations. So you put 200 here, then you solve for your x. That will be the corresponding x value. That will be the corresponding x. That will be the corresponding x value. That will give us this E here. So that's what the question wanted us to find. The question wanted us to find the excitation. Determine the excitation required. And I said the excitation is coming from what field current will go through the generator field winding. Give us the E. That will give us the voltage for this motor. That will cause the speed to reduce to 200. It's a lot. Just play back and then get this part. But it's not difficult. It's not difficult at all. We had a VH here, so we found the current going through the field. Once I had that current, I could find the power dissipated in the field. Now I want the power in the armature. So let me find the total power and subtract it from the field to give me the armature. Subtract the field from the total to give me the armature. Once I have the total power in the armature, P is IV, so I can find the armature current. I is P over V. Once I have armature current, I can find the motor back EMF. V minus IARA at 400. Then I'll use proportion to find the E at 200. So once I have the E at 200, that's the E of the motor here. That E is supplied from the generator. So the generator E plus the drops. Generator E will give us the drops plus the E of the motor here. So the E of the motor is becoming the V of the generator. That makes sense, right? Yeah. Say you have a generator like this. This is a generator. It has an E. It has voltage drop RA. Then the V is here. Do you get it? Now, so that this V, I've now put a motor there. So this V is now the back EMF of this motor. That's why that EG formula became EM plus IA array prime, because the array of this and the array of this will all account, will all come into the total resistance, because it's supplying through and then it's also supplied through here. So this is the total resistance here. The IA was the IA we found, the 990, and everything is set. Everything is set. So that's it. That's it for the chapter 1. What is the word, Leonard? We just take a time to do the reading part. Everything there's a reading part. Okay. Okay. So as I mentioned earlier, we are looking at controlling speed of DC separately excited or DC shunt motors by varying armature voltage. And then I said we have the conventional method, that is the Leonard control method. We also have the solid state control. That one makes use of the control rectifiers and the power electronic circuits. So control rectifiers and the chopper circuits and co. So we'll look at those ones later on. Those ones will be delved into details later on. Like we'll take them one by one and do with them. That's it. Here. So now let us look at controlling speed of DC motors by varying field current. By varying the field current. As we know that the speed is inversely proportional to the phi. It depends on IF. So if I'm reducing the IF here, I will increase the speed. I would increase the speed. And at this too, we'll look at the conventional method and we'll look at the solid state control method. Now let's see something here. Let's watch something here. Let's apply something we know already. Let's take a DC shunt motor. Let's take a DC shunt. Right. See, I have a DC shunt like this. My field is in parallel with my armature. I have a DC shunt like this. Right. Now there's some field current coming through here. There's an armature current going through here. Then I have my V here. Now you realize that look here. Realize that we know that what current chooses a path of least resistance, right? It means that if I have two paths, this path is 10 ohm, this path is 4 ohm. Most current to go through the 4 ohm. So it means that adding more resistance to a path reduces the current that goes through that path. See how we can apply that here. What that means is that if I add an external resistance to the field branch here, what will happen is that I've increased the overall resistance in this branch, and hence I'll reduce the field current. Once I'm reducing the field current, I am reducing the phi. And once I've reduced the phi, I will increase the speed. So we add an external resistance. I think it's called the field regulator. You add a field regulator in series with the field winding, and that reduces the field current, and that reduces the flux, and hence that will cause the speed to increase. So take the time to read. There's a lot of reading to be done. Right? How much can the speed increase to? The speed cannot increase infinitely. The speed can only increase up to a limit. The factors that control that limit is one is centrifugal force, the next is armature reaction, the next is so that is the properties of the motor will limit the maximum speed you can increase it to. Yes. So the conventional method, this is the conventional method here. That involves the conventional method. That one involves the use of the field regulator, right? So conventional method is you add a resistance in series with the field resistance as a means of reducing this current here. So that's it here. That's the conventional, the old method. Okay, traditional method. Alright. Okay. So you read. Here, let's see the effect it has on the characteristics. Now we know that it says P is equal to what? VA over K phi minus RATE over RATE over K phi squared. Now, here, as I'm varying the phi here, you can see that phi t is here. We mentioned that this is the slope of the line, right? So you can see that here the lines will not be parallel as in the first case. Here the lines will not have the same slope. So at this speed here, they will have different slopes like this. Like as if they are all converging at some point. Here, so here we have different slope because the slope is affected by phi here. So as I vary phi, I'll vary the slope of the curve. But I think in the first case, we were just varying the v here. So we didn't touch the gradient, so the slopes were parallel like this. The lines were parallel to each other like this. Hope that makes sense to you. Okay, so now let's look at the conventional method. We've done it already. So we say the conventional method is that you will add what? You will add a field regulator, an external resistance serving as a field regulator in series with the field winding, like this. So that because you've increased this total resistance here, you reduce the current that gets here. And as you reduce the phi, as you reduce the IF, you reduce phi, hence you increase speed. That's it. So let's look at the question. Okay. A 220 volts, 21 amps, 1000 rev per minute DC shunt motor has an armature resistance of 0.05 ohm and a field resistance of 220 ohm. The magnetization curve at 1000 rev per minute for the machine is given by the following. So we have the OCC curve here again. Plot the speed torque curve for the motor when no external resistance are included. So first case, no external resistance, right? First case is the normal one. So first case is like you have your RF here, you have your RA here like this. Then second case is plus an external resistance. So we know that once I'm adding an external resistance, I'll reduce the current, reduce the phi, and increase the speed. So that one is going to occur at a higher speed. That one is supposed to occur at a higher speed. Let's see. We know that speed is equal to what? So can you refer to the question from your phones? I don't want to be going back. Speed is VA over K phi minus RATE over K phi squared. I'm supposed to plot a speed torque curve. Speed torque curve. I have the VA. I was given the VA in the question. I've been given RA in the question. Let me find K phi. Let me find K phi. Let me find K phi. Okay, let's see. Now, I want to find K phi. I have the shunt motor like this. What the value of my RF? My RF is what? 220 ohm. RF is 220 ohm. My RA is what? RA is 0.05 ohm. 0.05 ohm. My voltage supply here is 220 volts. Now, let me find the magnitude of the field current. Let me find the magnitude of the field current. So from here I can tell that what IF is what? IF is VF over RF. VF is 220, RF is 220. That's 1 amps. IF is 1 amps. That means that if I'm able to plot a graph of K5 against IF, see it looks like this, and I come and find 1 amps on this curve here, I'll find the value of the K5 that's causing this to happen, that under this state operation. That's what I want. I want to find K5. But see, in the question I was given IF against E. I was given IF against E. But I said I want to plot a graph of what? IF against K5. But I know that K5 is equal to what? E over omega M. K5 is equal to E over omega M. So for let me just take, I'm just taking 3 points or 2 points. 0.2, 0.4, 0.2, 0.4, 50, 100, 50, 100. I'm just taking the first 2 points. So for each of them, I'll find the corresponding K5. Let me find my omega M. Omega M is what? Omega M, that is the motor speed, right? It was given to me in as 1000 rev per minute. So 1000 rev per minute. 1000 times pi over 60. So I'll get it. 1000 times 2 pi over 60. That is 104.71. 104.71. So it means that I divide each of these by, so here I'll do 50 over 104.71. Then here I'll do 100 over 104.71. And that's the value that I'll get here. If I get all the K5s, if I get the value for all the K5s, now I can now plot a graph of what? A graph of K5 against IF. So I'll plot a graph of K5 against IF here. K5 against IF here. And I'll come and match that. Okay, at 1 amp, what K5 will I have? And I'll come and put that K5 into omega is equal to RA. Omega is equal to VA over K5 minus RATE over K5 squared. So once I have now I have V, I have K5, I have RA, I have K5 squared. I'll just take values of the T. I'll just choose the T to be 1, 2, 3, 4, 5. And I'll find the corresponding speed values and I'll use it to plot. That's what that question wants from us. So that's what a question like this wants from us. So in a question like this, if you give it, you give us 2 points. You see, once it gives you 2 points, it's the equation of a line. Yeah, because the line is almost linear for some points. It's linear for almost all this region here. So if I give you 2 points, 2, 3, and 4, 1, you should find the equation of the line. Find gradient, find equation. And as such, any line you want to trace, let's say I have the equation of the line to be y is equal to 4x plus 1. It means I'll just put in the 1 in place of x here. And I'll find the corresponding K5 value. And I'll put that K5 value into the speed torque equation formula. This speed torque equation formula here. So that's it. So that's it. Should I even pause? I don't have pause. Should I pause somewhere? So right now, take time and just watch. So we found our IF. We use our tables to find our K5 E over omega M. You find all the K5 values. Now you plot IF against K5. And the IF you found 1 ounce. You come and find its corresponding K5. Put it in this equation here. Take any values of torque 1, 2, 3, 4, 5 and find the corresponding speed and you plot them. So kindly take your time and look at it. I'm giving you some time to look. Okay, so that's it. So that's it for the example 2. That's what was done. Then the same thing for the second case when they add the resistor here, and that I think is of 110. That resistor will affect the IF, right? So it will reduce the IF as we know. So it's now become VF 220 over 220 plus 110. So the IF will come down to 0.667. Once IF has come down, it's like the speed should go up. So IF comes down. So I come and choose this IF 0.667 here to find the K5. And I can put that K5 here. And then I can go ahead. So that's it. Obtain the corresponding K5 for this current. And hence the required speed torque curve as in A. Same as in A. This here. Find your omega M. It's the same thing. K5 is equal to omega M. Yeah. Alright. Okay. So so the same example, driving a certain load at 1000 rev per minute takes a current of 21 amps from the line. It is desired to raise its speed to 1500 rev per minute. So we are trying to raise the speed. So we need an external resistance. So find the value of the resistance that must be included in the field circuit when the load is a constant torque load. When the load is a constant torque load. First, let's find the torque. One, that's the torque at the 1000 rev per minute. Torque at 1000 rev per minute. The torque at 1000 rev per minute. So we know that torque is equal to K phi IA. Torque is equal to K phi IA. So IA in the question was what? The IA was, I think, was 21 amps. IA was 21 amps. Then the K phi that you found for the first case, when you match it. Guys, let me see. So torque is K phi IA. Right, I know that K phi is equal to what? K phi is equal to E over omega m. So at 1000 rev per minute, let me find what my E will be. My E will be equal to what? E is equal to V minus IA RA. The V was 220. IA is what? V was 220. IA is 20. See, because we found that in that condition, our field current was 1. So if it's drawing, let me show you. I have the shunt motor here. It's drawing a line current of 21. Field current is 1 amps. So armature current becomes 20 amps. So it becomes 20 amps multiplying RA. We were given RA in the question to be what? RA was 0.05. So when you do that, you can get your E here. Once I have my E here, I can find my K phi. And once I have my K phi, I can go ahead to find my torque. So that's how the thinking process is. Right? You want to find, they say it's a constant torque load. First case, constant torque load. Constant torque load means that TE2, the torque at the new speed, is equal to the torque at the initial speed. So first, let me find the torque at the initial speed, TE1. That torque is equal to what? K phi IA. That K phi is equal to what? E over omega m. E is equal to what? V minus IA RA. So get your E, get your K phi, get your torque. Once I have my TE1, I can find my TE2 because it's a constant torque load. Now we know that what? Now they said we want it to run at 1500. So speed is equal to what? VA over K phi minus RA TE over K phi squared. RATE over K phi squared. So here, what are we doing? We want to find the resistance that I'll add here. Right? So what I can do is that I have my VF here. I have VF here. Watch you. This is my total resistance, RT. So if I want to find, let me find the IF, right? If I find IF, then I can see that what my RT is what? RT is VF over IF, right? RT is VF over IF. So once I know RT here, I can subtract the field resistance to get the external one that I'll have to add. That will make sense, right? So all I can do is that I'll find, so we are still working with the same curve. So I'll find this K phi against IF. K phi against IF. So I'll find K phi, match K phi here to find the corresponding IF. So I have my IF here. I can do VF over IF to find R total and subtract the RF from R total to get the R external. So that's it. So that the proof value of K phi will give you IF from the K phi curve. And with IF known, the total resistance in the field can be determined. Once you have the total resistance, you can subtract it to get the external one to be added. Now let's see. Let me show you something. Here. Let me clean inside. So I'll do substitutions, right? So 1500, I'll change it to rad per second. So I'll put the value here. So that 1000, that's this times this here, right? Then I'll put my V there. V was 220. So the idea is that make 1 over K phi equal to a variable. So let's make 1 over K phi equal to M. That means that I'll have this value here. That's 2 pi times 1500 over 60. 2 pi over 60. That give me what? I have 157.09079 is equal to, now 1 over K phi is M. So I have Vm. That's 220M minus RA RA times, we know what TE was, because TE is equal to TE1. Then 1 over K phi squared. If 1 over K phi is M, 1 over K phi squared is what? M squared. Because you see my 1 over K phi all squared, that's M squared. So times M squared. I'll solve this quadratic equation here. I'll get my M here. I'll get M. Once I have M, I can find K phi from that M. And if I have K phi, I'll just go to the curve here. I'll go to the curve, find the corresponding IF. Once I know IF, I can find R total. R total is VF over IF. Once I have R total, I'll subtract this to get the external resistance I'll add. So that's it. That's it for that question. Like, I'm talking fast because a lot. So if there's something you don't get, just play back a bit and it will make more sense. Okay. Now the second condition is when constant power, right? Constant power load. So if I have a constant power load, it means that PE2 is equal to us PE1, right? And power is what? Times speed. So TE1 omega 1 is equal to TE2 omega 2. So means that my TE2 is equal to what? Omega 1 over omega 2 times TE2. Initially it was running at 1000 rev. I want it to run at 1500 of TE1, TE1 of TE1. So I'll get TE2 to be what? 2 over 3 of TE1. TE2 is 2 over 3 of TE1. 2 over 3 of T1. Now note that torque value you are finding, that's what you bring here. That's what you put here. That's what you put here. So here it becomes this. So once I find it, it's just the same process. You go through the same process. You go through the same process. So as we said, here too, what we learned is the conventional method. So there is a solid state control that makes use of power electronics. So usually they use a single phase semi-control rectifier. This is the formula for it. We'll get there. So like here, let's just skip it for now. I can't find the pause. So everything we've done so far, we're looking at speed control of DC shunt and separately excited motor. We saw by varying armature voltage to reduce the speed, and that is we saw conventional method, that's the one Leonard, solid state method. Then we came to speed control. Speed control by varying field current. And another one we saw the conventional method, that's the use of the field regulator and the state. Now let's move on to speed control of what? Speed control of DC series motors. Speed control of DC series motors. Speed control of DC series. how a series motor looks like, right? We have a field here in series with your armature, and then you have your voltage applied here. Over here, in this case, let's look at varying the armature voltage. Varying the armature voltage. You know that we vary armature voltage to what? To reduce the speed, right? Okay. Now, varying armature voltage. Conventional method when it comes to the solid state control. The conventional method here, here's what you do. Let's think of this. Let's add a resistor here. Let me call this Rx now. Now check out something. At first, the voltage drop here was, let's say, if the voltage here was 20 volts, right? Now, when I add a resistor here, what happens? The resistor causes a voltage drop. A voltage drop. So it reduces the voltage that gets to the armature. And once I can reduce the voltage that gets to the armature, I can reduce the speed. So that's what they do. Add, it's called the controller. It's called the controlling controller resistor. You put it there to cause voltage drop to reduce the voltage that gets to the armature. And once I can do that, I can vary the speed. Once I can do that, I can vary the speed. So that's it. So the higher the resistance that I add to the circuit, the more the voltage drop across it. Hence, the less the voltage that gets to the armature. And once I've reduced the voltage at the armature, I reduce the speed. So that's it here. So R3 is the highest resistance. So that has the smallest speed. I1 is the normal condition then. So that's it. That's what we have here. Then all these reading parts and everything. Okay, let's take this question. DC series motor with armature and field. Let me check how many hours we've done. So we'll look at this question in the next video. Okay, so look at it in the next video. Thank you very much for your time. Stop recording.